Okay, so let's take a look at the E2 reaction and cyclohexene formation. So the E2 requires the abstracted proton and the leaving group to be anti-periplanar. In cyclohexane systems, this requires the hydrogen and leaving group to be trans-diaxial. Okay, now why is this important? Equatorial groups are not in proper alignment, and a trans-diequatorial ring flip will give a trans-diaxial chair conformation, which will allow the reaction to proceed. Now, if we take a look at the following molecule, we have 2 protons, right? But we can end up in a situation where, in fact, only one of these protons is actually able or viable to react. So the equatorial conformation doesn't have an anti-periplanar arrangement of our proton and leaving group. So this is a not reactive conformation or non-reactive conformation. The only time you have the requisite trans-diaxial arrangement of the proton and your leaving group is if your proton and leaving group are trans-diaxial. And now as we see, we have 2 trans-diaxial or anti-periplanar protons, and thus we can form a double bond on using either of these protons. So only when you have this trans-diaxial arrangement can you undergo an E2 reaction. Does that idea make sense?
Yes.
Perfect. Okay. So just to show this through a Newman projection, in the trans-diaxial arrangement, just like when we looked at Newman projections, the hydrogen and chlorine are anti-periplanar to each other, and as a result, they have the requisite geometry for an E2 reaction. When our chlorine is equatorial, there's no way for you to end up with an anti-periplanar hydrogen, and as a result, there's no reaction in this conformation. Now, this is immediately going to spring to mind this idea where certain molecules are more reactive than others simply because they can more readily access this trans-diaxial arrangement. So, the only way the leaving group and CH bond can be anti-periplanar is if they're on opposite faces of the ring, right? So, for example, if you have 2 choices of protons, do you notice how we have a proton in red and proton in blue? Looking at our chair conformation, let's just draw this chair conformation together. So the methyl is up, the bromine is down. Let me just make sure I'm not drawing did he draw the enantiomer? Well, let's look at this. So the methyl is up, the bromine is down, hydrogen is up. So this is our first conformation, and then after a ring flip, we have our second conformation. Okay, so as we can see in our in one of our conformations, we have this trans-diaxial. Let me circle this in blue so that way the correlation stands as it should. So this proton in blue is trans-diaxial and anti-periplanar compared to our leaving group. So as a result, what we can see very clearly is in both of these chair conformations, only one of our protons, this proton in blue, has the requisite geometry, has the requisite anti-periplanar arrangement relative to our leaving group for elimination. Thus, elimination can only occur Elimination can only occur between C1 and C6. Elimination only occurs with this proton in blue. That's why we only get a single regioisomer. So the E2 reaction is not just stereospecific, it is also regioselective. Only the proton that has the trans-diaxial arrangement with our leaving group can eliminate efficiently. Now, one other point that I'd like us to appreciate, if we look at this conformation, with the trans-diaxial arrangement, is this conformation that I'm sort of indicating clearly here, is this conformation the highest or lowest energy conformation for the two possible chair conformations? Is it the highest or lowest energy? What do we think? Looking at this conformation with the trans-diaxial arrangement, is it the highest or lowest energy conformation?
Wait, sorry, I missed out.
So
Are you talking about the one on the left or the right?
The one on the left.
The one on the left, that's the lowest one, because the one on the right, they have multiple. Is that the methyl group?
So
the methyl and the bromine.
Okay, so you're talking about this. You're talking about this structure right here.
Sorry, my dogs are playing. No, I was talking about the one below it. I'm sorry.
So this one. So if we compare these two structures, as we notice in the first structure here, the structure where we have our proton and our leaving group circled in blue, we have an axial methyl and an axial bromine, right? And because we have all of these groups axial, we have a large amount of 1,3-diaxial interactions. And as a result, the reactive conformation is actually our highest energy conformation. Does that idea make sense to everyone?
Yeah, thank you.
And now this is something to appreciate, because depending on the barrier for this ring flip, that determines how quickly this desired E2 reaction can occur. Now let's look at another example. In this case, we've just modified our stereochemistry slightly. But even subtle differences in our stereochemistry can result in dramatic differences in how the reaction plays out. Now, if we look at the following molecule, we see that rather than just having a single viable proton for elimination, we have two viable protons that can eliminate. And as a result, we have two potential products. Now, the main issue with this, and the way you determine which of the products is actually formed, is by utilizing Zaitsev's rule. Remember, when we looked at the energy diagrams and we looked at the rate of reaction for these various E2 reactions, we found that the reaction that generates the more substituted alkene is not only the kinetic product, it's also the thermodynamic product. So it's favorable to eliminate to generate the more substituted alkene. So of these two possible products, why is the product on the left formed exclusively? What's the difference between the product on the left and right? Why do we not generate the product on the right in substantial amounts? If we're invoking Zaitsev's rule, which of these products is preferred? The one on the left or the one that I crossed out on the right? What do we think? So as the product on the left has the most substituted alkene, this product is preferred. Does that idea make sense to everyone? So if you have multiple trans-diaxial protons, then elimination will occur to favor generating the most substituted alkene. So first you think about geometry, then you think about the substitution of your alkene. So just to summarize this, if multiple trans-diaxial hydrogens are present, the more substituted alkene is favored. Okay, so now is where we start to add some nuance to this discussion. We've already established that the leaving group in hydrogen must be trans-diaxial for E2 reaction to occur. Thus, a ring flip is often required to generate the less stable trans-diaxial conformation. The barrier to a ring flip and the amount of trans-diaxial conformation at equilibrium depends on the difference in energy between the axial and equatorial conformations. So, for example, looking at this molecule, we get the following chair conformation. As we notice, if our bromine's equatorial, we can't have a trans-diaxial arrangement by definition. After a ring flip, we end up with our methyl and bromine axial, and we have two trans-diaxial hydrogens to choose from. One thing that I'd like you to note is that this conformation is the higher energy conformation. So at equilibrium, we're not going to have a ton of this conformation, but we'll have enough for appreciable reactivity. Now, if we wanted to compare these two substrates and ask ourselves what substrate reacts faster, we have to think about the reactive conformation and how easy it is to access this conformation. So notice, with just a minor change in stereochemistry, after our ring flip, we still have our trans-diaxial hydrogens, but because our methyl group is equatorial, this axial conformation is the lowest energy conformation. Now you may say, big deal, why does this matter? Well, this can change a reaction from taking a few minutes to taking a few hours. And the bottom reaction is substantially more favorable and occurs substantially faster. And the reason why the bottom reaction will occur more quickly is because it goes through a more stable chair conformation. We have more of the reactive conformation at equilibrium, and as a result, the reaction proceeds to completion more readily. Does that make sense? Can I get some confirmation that everyone understands that principle? The lower in energy your reactive conformation and the easier it is to access your reactive conformation, the faster the rate of E2 reaction. So as just a general rule, the greater the amount of diaxial conformer and the lower the relative energy of the diaxial conformer, the faster the rate of E2 reaction. Okay, let's look at an example. In this case, we're asked to predict the product of the following reaction, draw the chair conformation that reacts, and draw a mechanism for the reaction. Okay, so first things first, we need a chair conformation here. Oops, that's not good. Okay, perfect. Okay, so our bromine is pointing up, so we'll draw it as axial. Our methyl is pointing up, so it's equatorial. Okay, so we have two possible protons. We have a proton in red that I'll call A and a proton in blue that I'll call B. These are our two trans-diaxial protons. My question to you is, which proton will react overwhelmingly? which proton will overwhelmingly react. And to help us think this through, it's important to consider what possible products we'd make. So one of our possible products looks like this. The other possible product looks like this. And we only generate one of them. So we see students typing in the chat, this blue proton is going to be selectively deprotonated. Would someone like to provide a reason why? Why is this blue proton being removed? So you see students typing, the blue proton will be removed because it generates a more substituted alkene. And that's exactly right. Following Zaitsev's rule, in general, it's the reaction that is geometrically allowed that will generate a more substituted alkene is favored for E2 eliminations. So we're going to pull off our proton and we're going to kick out our leaving group and we'll exclusively generate the following product, B. So we only generate a single regioisomer, and that's due to the stereospecific and regiospecific nature of the E2 reaction. Does that idea make sense? Perfect. So let's now attempt the following example. All I've done is change the stereochemistry, but the nature of the problem has changed quite dramatically as a result. So I'd like you to take a look at the following molecule. I'd like you to predict the product of the following reaction, draw the chair conformation that reacts, and draw a mechanism for the following reaction. And just to showcase a set of possible products to spark our discussion, would we generate product A or B? Or another product that I'm missing on this chart? So let's take about 5 minutes to work through this problem. Ideally, I'd like to see some students drawing out the chair conformation using the annotate tool. So let's work through this example and let's try to comment on whether we'll form product A or B. And I'd like to see a student contribute either a photo or an annotated chair conformation for the following reactive conformation for this E2 reaction. So would anyone like to draw a sample chair conformation? Would anyone like to draw the two chair conformations and indicate the reactive conformation? So what does the class think? Would we generate elimination product A or B? Would you be able to start vocalizing your thoughts in the chat or verbally? Or if you have a question, don't be shy to ask it in the chat or verbally. What do we think? What's our thought process looking like right now? Does anyone have a proposal or question for this segment? Does anyone have a proposal or question for this problem? Well, so if we were looking at these chair conformations, so the first of which, so we have our bromine axial, and our methyl group is pointing down axial. So looking at this structure, which proton is trans-diaxial? Which proton is trans-diaxial? Proton A or proton B? Which of these protons has the requisite geometry for elimination? A, exactly right. So following this, only proton A will selectively undergo an E2 reaction, and in turn, we will selectively generate product A as a single product. Does that make sense to everyone? So you need the requisite trans-diaxial arrangement of your proton and leaving group in order for an E2 reaction to occur. Does this example make sense to everyone? Perfect. Okay, so let's keep going now. And let's try to apply what we've learned to the following example. So in this case, which of the following molecules will have a faster rate of E2 reaction? And I'd like you to draw both chair conformations to justify your answer. And I'd like you to tell me what products form from E2 elimination of each substrate molecule. Now, this is very much in the style of a common ACS or exam question, where you're asked to look at a substrate, draw a chair conformation, and analyze which of these conformations is lower in energy or higher in energy, and in turn, which of these conformations will react more readily and more efficiently and quickly via an E2 reaction. So I'd like you to take a look at these two structures. There's plenty of space below for you to draw out the 4 chair conformations needed to have this full discussion. And I'd like to see some proposed product structures drawn. I'm not going to fill in the products for you in this case because part of the sort of reasoning aspect of this problem is figuring out which products are actually viable to generate. So let's work on this example, and I'd like at least a few students to share their responses using the annotate tool or as a picture in the chat. Don't be shy to ask a question or share your comments in the chat or verbally, and I'd be happy to draw out and verbalize any of your comments and convey your comments onto the class whiteboard. So let's work on this example, and Then we'll discuss in about 5 to 6 minutes. Would anyone like to share a picture or annotated response for this question? Would anyone like to contribute a chair confirmation using the annotate tool as a photo? Does anyone have a proposal? Would anyone like to suggest which of these substrates, A or B, will react faster and what products we will get out? Or does anyone have a question? It's perfectly fine to advance the discussion via a question. Does anyone have a question that I could respond to that would help as you work through these problems? So I'll give everyone a little more time and then we'll discuss in about another 1 to 2 minutes. It's really important that when we do these problem solving exercises, that you come up with your proposed response before viewing the solution. So that way you can revise your logic once we discuss the example together as a class. Okay, so let's take a look. So this first conformation, so for structure A, let's draw one of our chair conformations. Okay, so we have our chlorine axial. This isopropyl group is equatorial. What do we know about the isopropyl groups? Do these isopropyl groups prefer to be axial or equatorial? Do these isopropyl groups prefer to be axial or equatorial? Equatorial, right? So we have a strong preference for placing this isopropyl group equatorial. Okay, finally we have this methyl group. And this methyl group is axial as a result. Oops, wrong spot. Right here. Okay, the hydrogen's axial, the methyl's pointing down, so the methyl group is equatorial. Okay, perfect. So this is the conformation for structure A. Looking at our trans-diaxial arrangement, we have two possible protons to choose from, right? Again, same drill, proton A, proton B. Which proton is going to be selectively removed, A or B? which proton will the base abstract? A. And why is that? Why is that? Why are we selectively removing proton A? The alkene would be more substituted as a consequence of the carbon being more substituted. Yeah. Focus on the alkene substitution rather than just carbon substitution, because it's the alkene stability and alkene energy that determines the transition state energy and why this reaction occurs so readily. But yes, your logic is perfectly reasonable. Okay, so we have the following product generated. Perfect. So this is the product from substrate A. Let's look at substrate B now, as substrate B is a little bit interesting. And I'm going to give myself some space because I'm going to have to consider the ring flipped form. Okay, so again, we have this isopropyl group, equatorial, except this time our chlorine is also equatorial. It's pointing down. Now that may not seem like a big deal at first glance, but it introduces a pretty dramatic change in how this reaction proceeds. So, looking at this current conformation for structure B, can this conformation that I'll call conformation 1, can this conformation actually react via an E2 reaction? It can't, right? There's no trans-diaxial arrangement. So we have to view a ring flip. And you'll notice by how I'm drawing the arrows that I don't have a positive impression of our product, of our second conformation. It's not a product, it's just another conformation. Okay, so in this case, we have our chlorine axial. So things are looking up somewhat, but we've introduced a bit of a problem here. Just a mild problem of having this giant isopropyl group axial. So if we compare conformation 1 and 2, which conformation is lower in energy? Which conformation is lower in energy? Conformation 1 or conformation 2? 1, yeah, conformation 1 is lower in energy. So as we can see, conformation 2, our reactive conformation, is high in energy and present in small amounts. As a result, if we compare substrate A and substrate B, which of these substrates can more readily access the reactive conformation? Which of these substrates can more readily access the reactive conformation? A. And as a result, the reaction to generate product A occurs faster. So we have a faster reaction because we have a lower energy reactive conformation. Note, when we say lower energy reactive conformation, we're not directly comparing A and B. We're looking at, if we had to choose for substrate B, we see overwhelmingly that the reactive conformation is higher in energy and less favored to be generated. We have less of the reactive conformation floating around, so our reaction rate is slower. So when you think about the amount of a reactive conformation, always compare the two chair conformations and think, is my trans-diaxial conformation easy to form or difficult to form? Is it high or low in energy compared to the equatorial conformation? Okay, so suppose we do generate the conformation number 2. We only have one proton, so that's a pretty straightforward, E2 elimination. And as a result, we end up cleanly, well, assuming only E2 occurs, we end up cleanly generating a single product. So, you know, if you're willing to wait, I guess this reaction could be viable. What? Sorry, the methyl's in the wrong spot. Just for completeness, it should be here. Because it was pointing down in the original substrate. Okay, so we end up getting a single product out from substrate B. So even though it's slow, the reaction of substrate B does generate a single product with regio and stereo control. Assuming, of course, E2 reactions are the only pathway that we can go through. Does this example make sense to everyone? Does this example make sense? This is sort of a textbook analysis of structures and reactivity and reactive conformations that makes for pretty good exam questions or ACS questions. Any other questions on this example? You compare the equatorial and axial conformations for each of your structures. And then you ask yourself, is my trans-diaxial conformation for my structure lower or higher in energy than the equatorial conformation? The easier it is to get to the trans-diaxial reactive conformation, the more of that species you'll have floating around at equilibrium, and generally the faster your reaction rate will be. Does that make sense? Perfect. Okay, so let's keep going now. And in this case, we're going to look at a reaction that has relevance, and you'll see this a ton in the next organic class, which is the E1CB reaction. It's a stepwise reaction where an acidic beta proton is deprotonated by the base to yield a stabilized anion. Finally, we have an elimination of the leaving group to yield an alkene. Okay. So we have a deprotonation step followed by elimination. The second step in the E1CB is rate limiting, and E1CB reactions are accelerated if the leaving group is good and the beta proton is acidic. So let's talk a little bit about the E1CB from an energy diagram perspective. So elimination of the leaving group is the rate limiting step. That's step 2. So in step 1, we are removing our proton. So for example, we have our substrate with the leaving group. We have our electron withdrawing group, and we have our proton. And in the first step, our base is removing our proton. So in our first transition state, we're looking at deprotonation. We're not too concerned about this deprotonation step because it's not rate limiting and doesn't really affect the reaction outcome substantially. Looking at the second step, once we have our anionic intermediate, for our second step, we are forming our alkene. And breaking our carbon leaving group bond. So this concerted step, you can draw it sort of like this, where we are breaking our carbon leaving group bond and forming our alkene. So this is our rate limiting step as it has the largest activation energy. Does this make sense to everyone so far for the E1CB reaction? Okay, so let's look at an example. So for example, if you have a proton adjacent to these CF3 groups, which are very effective electron withdrawing groups, and you have a base on the adjacent carbon, you can deprotonate. You can deprotonate and generate your anionic species. So once we have our carbon-centered anion, we then can eliminate our leaving group and generate our alkene product. Does that make sense to everyone? This is a stepwise process. It is a two-step mechanism. Do not draw it as a single step. That would be implying an E2 reaction, which has an entirely different reaction coordinate. So examples of an E1CB reaction, we can look at dehydration after an aldol condensation. Yeah. So in this case, we kick down our lone pair and we kick out hydroxide. Even though it's a poor leaving group, you can kick it out, although it's quite slow. You can also look at, for example, the elimination of a vinyl halide to yield a substituted alkyne. Perfectly reasonable. So let's do some product prediction now. So we're asked to predict the product from the following reaction. We're treating our molecule with a non-nucleophilic base and looking at this ester functionality. This looks like a pretty good electron withdrawing group, right? I mean, this pK is about 30. But even if the actual deprotonation step doesn't favor the product, if you can generate a little bit of your anion, that anion can then eliminate. So your triethylamine is going to go in and it's going to pull off this proton. We're going to generate our stabilized anion. And I'm going to draw equilibrium arrows because this is an equilibrium. And then we just kick out our leaving group. So at the end, we get the following product. Which is an acrylate, which is quite useful for a range of reactions that we'll learn later on in organic chemistry too. Though this substrate in particular would not be very fun to make in the lab because it's a pretty strong lacrimator. So certainly not something to be prepared outside of a fume hood. Does this mechanism and product prediction make sense to everyone? Any questions on the E1CB reaction? Perfect. So let's take a moment and I'd like you to predict the products from the following reaction and draw a mechanism for this reaction. And I'd like you to tell me, of our possible products, which one will we make? So I'll give you a list so that way you can respond with just a letter in the chat and that'll give me a sense of what the class is thinking. So would we generate this product, B, or product C? What do we think? A, B, C, or none of the above? Which product would we expect to see from this reaction? And if you're having a question, don't be shy to ask a question in the chat as well, or verbally. Additionally, you can also use the annotate tool and try to share your proposed mechanism for this reaction. What do we think? What product will we get? Does anyone have a question on this problem? I'd like to see at least a few student responses so I can get a sense of what the class is thinking. Which of these three products will we expect to make from this reaction with triethylamine? Which of these three elimination products would we expect to generate if we're thinking about E1CB elimination patterns? And if we're thinking about the E1CB and we're thinking about which proton is easier to remove, is proton A or C in terms of pKa values? In terms of pKa values, which of these protons is easier to remove? Does that pKa value hint help? A is easier to remove, right? We have a pKa of 30, pKa of like, I don't know, around 40 to 45. Pretty hard to remove. So then A is the most acidic proton. So we are going to remove our most acidic proton and generate an anion in small amounts. However, once we have our anion, we're ready to go and we can proceed with the second elimination step. An interesting thing about the E1CB reaction, it doesn't necessarily require the strongest base. Okay, so we have our anion, and now we can kick our anion down and kick out our leaving group. And that in turn gives us exclusively product A. Does that logic make sense to everyone? This is a pretty useful reaction for generating substituted unsaturated ketone functionalities. Whoops, sorry about that. Yes, it's product B. Let me cross out A. Yeah, so we only get out product B. Does this make sense to everyone? So this is classic E1CB. We deprotonate the most acidic possible proton, and then we eliminate our adjacent leaving group. Does this example make sense? Perfect. Okay, so let's keep going now. And let's look at the E1 reaction, which is honestly a bit of a mess. So the E1, just like the SN1, is unimolecular. The rate depends only on our substrate concentration. Okay, that's already starting to give a bad sign. The reaction rate increases with substitution. Primary is slower than secondary, which is slower than tertiary. Now, here's where the E1 and SN1 reaction in many cases end up really giving you a ton of problems, in that the E1 reaction competes with the SN1 reaction. So when you try to run an SN1, you get some SN1, and you invariably will get a little bit of E1. SN1 and E1 are typically observed as mixtures, SN1 and E1 products. It's very hard to selectively get only substitution or only elimination, though you can tip the scale by careful adjustment of conditions. For example, the conditions that the student ran this reaction under invariably are going to provoke a little more elimination than usual. Does this idea make sense, that SN1 and E1 reactions are competing with each other? Okay, so let's talk about the E1 mechanism. So first, just like in the SN1, the leaving group leaves to form a carbocation. And second, a proton is removed by the base to give an alkene. And I'm going to put base in quotes because remember how we talked about the pK of different protons? What is the pK of this proton adjacent to a carbocation? What is the pK of this proton, roughly? If water is able to remove that proton, what do we think? What's the pK of that proton? Or even at a superficial level, would we expect this proton to be acidic or basic? What do we think? Proton adjacent to a carbocation. It's pretty acidic, has a pK of around -1 to 1. So it's quite acidic, quite easy to remove. And so in turn, any functional, any remotely competent base can remove that proton. Now, there are a few things to keep in mind. The rate determining step is the loss of the leaving group to form our carbocation. This is exactly the same as the SN1 reaction rate limiting step. The rate is proportional to carbocation stability. And because we're going through a carbocation intermediate, SN1 byproducts can be observed. Does that idea make sense to everyone? Any questions on this overview? Okay, so let's keep going now, and let's talk about the E1 energy diagram. And the way I like to think of the E1 energy diagram is that the first step is identical to the SN1 reaction. It's almost like the first step is exactly the same as the SN1 reaction. So in step 1, we have, for example, our leaving group. And in step 1, we are losing our leaving group and we make a carbocation intermediate. The transition state for step 1 is carbocation-like, in that we are building up partial positive charge as our leaving group leaves. Does that make sense? So the first step is rate limiting. So step 1 is rate limiting or rate determining. In step 2, we have our carbocation and our base is removing our proton in order to generate our alkene. Both of these steps are exergonic. And as a result, our transition state is going to resemble our reactants. Oh, sorry. Step 2 is exergonic. Step 1 is endergonic. And that's why the transition state for step 1 resembles our carbocation. Does this energy diagram make sense to everyone? Does this make sense to everyone so far? Okay, so again, step 1 is rate determining. And the elimination step is fast. Okay, let's talk a little bit about substrate effects, as these are pretty important. So the reaction rate increases with substitution, and most importantly, this is a consequence of the fact the reaction rate increases with carbocation stability. Just remember, allylic and benzylic carbocations are especially stable. So if you have like a primary benzylic or primary allylic substrate, that can certainly undergo an E2 reaction if there are available protons. Second, polar protic solvents, just like for the SN1 reaction, stabilize the carbocation-like transition state, resulting in a faster rate of reaction. Finally, the better the leaving group, the faster the rate of reaction. So again, here's our energy diagram. So the leaving group and the substitution are primarily going to influence the activation energy for step 1. Okay, now here's where we talk a little bit about the SN1 versus E1 reaction. So the SN1 and E1 reaction proceed through the same intermediate. So in this case, so let's suppose we have our leaving group. In step 1, we kick out our leaving group. Wonderful. Everything's going as planned. The only problem is once we reach this carbocation, we've already crossed our rate limiting step, right? We've already crossed our rate limiting step, right? So then once our carbocation is generated, we can react via either pathway. So either pathway can occur. And the product distribution partially depends on the difference in activation energy between pathways. But to be perfectly honest, you're not going to get a ton of differentiation between these two pathways. You're going to get a mixture. Okay, so in the E1 pathway, we have our carbocation and our base, which in this case will be ethanol, will facilitate the elimination. And so if we're looking at our transition state for this, we are forming our bond and we are removing our proton. For the SN1 reaction, we just have our carbocation intermediate and our nucleophile is just attacking that carbocation. Okay, so because we're past the rate limiting step, once we get our carbocation, we just get a mixture. There's some ways we can bias this selectivity, but you're invariably going to get a mixture. There's not enough of a difference in activation energy, nor is the second step rate limiting. So as a result, you can't get any sufficient selectivity between substitution and elimination. You'll always get a little bit of each. Does that make sense? With that said, you can favor certain reactions. So SN1 products are favored if a strong nucleophile is present and the reactions run at low temperatures. Likewise, E1 products are observed if we have very weak nucleophiles and the reaction is run at high temperatures. Just like we brought about in our discussion of substitution versus elimination, elimination is favored at higher temperatures. Does that make sense to everyone? Perfect. So let's keep going with this. And let's talk about the regiochemical outcome of the E1 reaction. So E1 reactions prefer to generate the most stable, most substituted alkene. However, mixtures of regioisomers and stereoisomers are observed. So for example, if we take the following substrate and we treat it with ethanol and heat, we in turn would end up generating a mixture of regioisomers and stereoisomers from elimination pathways, as well as a substitution product. In general, the E isomer is preferred and the most substituted alkene is preferred, but mixtures of products are unavoidable. So for example, these highly substituted alkene products are going to be our major products, but inherently we're going to get a mixture. Does that make sense? Perfect. So when we compare the E1 and E2 pathway, a strong base is needed for the E2 pathway, but not for the E1. The E2 pathway is stereospecific, the E1 is not. E1 primarily will give the Zaitsev product. So for example, under E2 conditions with concentrated base, we only observe elimination when we have the requisite trans-diaxial arrangement of our proton and leaving group. Comparatively, if we run the same elimination under E1 conditions, we'll predominantly generate the Zaitsev product, which results in the more substituted alkene. So as we can see, the E2 and E1 pathways have different product preferences in many cases. Does that make sense? Perfect. Okay, so let's do an example. We're asked to draw a mechanism for the following E1 reaction and predict the products of the following reaction. Okay, so now that we have this idea set up, now that we have our problem arranged, let's go through each of the steps for the mechanism. So in the first step of the E1 reaction, we lose our leaving group. In the second step, we can eliminate and remove our proton. So ethanol will remove our proton and we generate our requisite alkene. Of course, we'd also see the other regioisomers as products of this reaction. And we would also observe a minor product of substitution. So we inherently will observe a mixture of products, with the following highly substituted alkene being the major product as it follows the Zaitsev rules. Does that make sense? Perfect. So let's keep going now. And I'd like you now to try to predict the products of the following E1 reaction when we treat this cyclohexane substrate with methanol and heat. And don't be shy to use the annotate tool to share your responses. You can also share a photo of your response as well. Does anyone have a proposal for the product generated from this reaction? Would anyone like to share using the annotate tool the proposed product from this elimination reaction? Yep, that's one of the possible products, and that in fact is the major product. Perfect. So let's clear and let's talk through this example. So first things first, from our mechanism, the first thing we're going to do is we're going to lose our leaving group. Then what we are going to do, and you can see some carbocation shifts in this case. You can see some carbocation shift behavior, but we're going to assume this substrate is well behaved. And we'll just eliminate our proton and we'll generate the following alkene as our major product. We'll also observe some minor products as so. And we can even see a small amount of substitution. So this reaction is going to give us quite a mess, with this product being the most substituted alkene, the Zaitsev product being major. Does this make sense to everyone? Perfect. So what we're going to do is we're going to take a quick 10-minute break and resume this discussion in laboratory. So I'll pause this recording